Hello. We're now going to look at the final category of artifacts in ultrasound imaging, and this is artifacts that relate to the beam path. The ultrasound machine in forming the image assumes that the beam is a straight line and that the ultrasound always travels along that straight line and therefore echoes come from on that straight line. So this talk is about artifacts that occur when that assumption is not correct. We will look at refraction, mirror image artifact, and then one other category that we will just look at briefly is artifacts related to equipment faults and electrical interference. So coming back to the main category of beam path artifacts, we'll look first at refraction. This is the diagram that you have seen before. So we have an ultrasound beam passing through a tissue interface between two tissues that have different propagation speeds. So the beam is deflected and travels in a slightly different direction. The machine assumes that the beam has continued on in a straight line, as I've shown with the broken line. So when the refracted beam strikes an object, such as I'm showing in this diagram, the machine is going to display that as if the beam had not been refracted. The machine, after all, has no way to know that refraction has occurred. So the question is, how serious is this? How much of a difference does it make to the image? And the answer is that normally, when you take typical values and calculate the amount by which the image will be incorrect, you find that the position of an object is likely to be displaced by a very small amount, maybe 1 to 3 millimeters. Since all of the tissues around it will also be similarly affected, this actually produces very little distortion in the image and normally is quite unimportant. However, there are specific situations where refraction causes quite dramatic artifacts. Let's take a look at that. One of the classic places where this occurs is when you're scanning transversely on the abdomen, and it is caused by the presence of the rectus abdominis muscles. These muscles are essentially lens-shaped when they are scanned in cross-section, and given that they are likely to be surrounded by tissues with different propagation speed, often significant fat, there is therefore the opportunity for the beam to be significantly refracted. So let's look at what happens. On the left, we have the beam, which I've represented with that single blue line, and it's being refracted. I'm showing that striking an object, and just to be specific, let's say that that is the superior mesenteric artery in cross-section, because this is a typical situation likely to be encountered. Now, the machine thinks that the beam has carried on in a straight line, as shown by the broken line, and so it displays that SMA in the position that I've indicated with the black circle. On the right, the beam has scanned further around, and now it is refracted in the opposite direction by the other muscle. Again, it scans the superior mesenteric artery. Again, the machine assumes the beam has carried on in a straight line, and therefore it displays the SMA to the right of its true position. And so we've essentially got the SMA being displayed to the left and to the right of its true position. So there's a doubling of that caused by this particular effect. Note that I have exaggerated the amount by which it is displaced, just simply for clarity in this diagram. Here's an example. In the image on the left, I have highlighted with the red circle what appears to be two superior mesenteric arteries lying side by side. On the right-hand side, the probe has been moved off-center so that the symmetry, the specific geometry that caused that doubling no longer exists. So we've just simply moved off the center line, and now we can see there is actually just a single superior mesenteric artery. So this is one situation where this does quite often happen when you're scanning on the abdomen and the effect is being caused by the rectus abdominis muscles. The other place where it is quite commonly seen is when scanning the heart transthoracically, where the cartilage and muscles associated with the ribs can cause refraction of the beam in two different directions, causing a doubling of some structures within the heart. So this is a fairly uncommon, but nevertheless potentially quite deceptive artifact. The other major artifact in this group is the mirror image artifact. As the name suggests, this is essentially the same as when you are looking at something being reflected in a standard mirror. In the case of ultrasound, we have highly reflective tissues acting as a mirror, and then objects that are really in front of the mirror are going to be duplicated and appear to be behind the mirror. If you think about an optical mirror, the mirror in your bathroom, if you're standing 1 meter in front of that mirror looking at the reflection of your face, the face appears to be 1 meter behind the mirror. We don't normally think of it that way, but it's exactly the same as what is happening here with the ultrasound. The mirror image is going to be displayed deep to the reflective mirror. Here's the geometry. And just to be specific, let's assume that we are scanning in the liver and the reflective tissue is the diaphragm. The diaphragm is normally very reflective because it normally has air-filled lung behind it. So it's essentially a soft tissue air interface. So the ultrasound will follow the path I've shown in blue. So the ultrasound comes down, strikes the diaphragm, and reflects back into the liver. Let's suppose there's an object, which I've shown with a red dot, and that produces an echo. The echo will then travel back along the same path as the transmitted ultrasound. So it will go down, reflect off the diaphragm, and then travel up to the probe and be detected. The machine assumes that the beam has carried on in a straight line, and it calculates the depth of that object by looking at the arrival time of the echo, which relates to the total path distance the ultrasound has travelled. And so this object is going to be displayed, as I've shown in this diagram, deep to the reflective interface and on a straight line based on the assumption that the beam has continued in a straight line. And so we get objects that are within the liver being displayed as mirror images deep to the diaphragm. Here is an example where I have highlighted with the white circles the object and its mirror image, and I've also highlighted with the arrow the diaphragm, which is the actual reflector. So you will see that that echogenic mass within the liver has been replicated deep to the diaphragm. You'll also notice there appears to be a whole lot of liver tissue behind the diaphragm. That is entirely mirror image artifact. So that is unlikely to be real tissues. Occasionally, of course, the lungs may not be air-filled, so if there's pathology, you may actually see real tissues deep to the diaphragm, but in general, it is routine to see this mirror image of liver tissue appearing deep to the diaphragm. In this particular case, as I've shown you, there's a mass and it's being replicated. So let's look at the geometry. So again, the blue line represents the ultrasound pulse, travels down that pathway, bounces off the diaphragm, back into the liver, strikes that echogenic mass, echoes from that mass, travel back down to the diaphragm and back up to the probe. The machine thinks that the ultrasound has travelled on down the line I've shown in yellow, and therefore that's where the mirror image is displayed. Now, this is actually a special case. Normally, you don't see an object in its true location and the mirror image of that object in the same single image. It's much more common that you have to scan backwards and forwards to identify the actual source of a mirror image artifact. And the reason is shown in the next slide. Generally, a reflective tissue is going to be at some angle to the scan plane, as I've shown here. So on the left-hand side, I've got a simple drawing. On the right-hand side, we are looking side-on at the scan plane. So up at the top, we have the transducer, and then we're looking at the scanned plane, and I'm showing the angled reflector. So what you can see is that when the ultrasound reflects off that reflector, it's going to reflect outside of the scan plane, outside of the scanned volume, and it'll strike an object such as the one I've shown here in this diagram. Notice that that object is well outside the scan plane, and therefore it won't be displayed in its true position. So we will only see the artifact, and I've shown where the artifact will be displayed based on the machine's assumption that the beam has continued in a straight line. So this is the more common situation, where you can see a mirror image artifact, and you then have to move the scan plane backwards and forwards to identify where it's coming from. Let me show you an example. This is the same mass as previously, but now the sonographer has just chosen some arbitrary plane through the liver, and you can see that as the probe is scanned backwards and forwards, we see either the object within the liver, or we see its mirror image artifact deep to the diaphragm. But we do not see both of them at the same time. So this is the more general situation. So if you had captured just a single still image, you might have something that looks like this, and it would be impossible for the person looking at this image to know whether that was a mirror image artifact or a real mass at that location, because they can't see where it's come from. So that's something that highlights the fact that sometimes it's only the dynamic scan which can tell you the full story. This is another thing to remember with mirror image artifacts. We've got here a very substantial mass in the liver, and then its mirror image artifact deep to the diaphragm again. But notice how different these two things are in shape, and this is due to the fact that we have a curved mirror. So we're looking at the reflection in a curved mirror, and just as with light, that's going to produce a distorted image of the mass. So whenever the reflective tissue is curved, you have to expect that the mirror image will be distorted. Now we have just this one example of what happens if you have an equipment fault. Now naturally there are a variety of different faults, and in this case we're looking at the effects of a damaged transducer. On the left we have a normal scan with a properly functioning transducer or probe. On the right we have an image produced with a damaged probe, and you can see two bands where the image is darker than it should be. If you were to slide the transducer around on the skin surface, you'd find that those dark zones remain fixed relative to the probe, highlighting the fact that it's an equipment fault, nothing to do with the anatomy. And finally, this is just one example of electrical interference. If we were looking at this dynamically, almost certainly that interference pattern would be moving, and it would be very obvious, and it is even obvious here from this single image, that that is not anything real. It is simply interference due to some sort of electrical equipment. And so, in summary, we have looked at this final group of artifacts, mostly relating to the beam path. So we looked at refraction, which is normally relatively unimportant, but can produce that ghost artifact, that doubling of structures, in which case it can be potentially misleading. We looked at the mirror image artifact, which is quite common, in fact very common. And we looked briefly at equipment faults and electrical interference, which are generally going to be quite easily recognized for what they are. So that brings us to the end of our discussion of artifacts. Just remember that artifacts are common. In fact, really, there are artifacts in every single ultrasound image. Some artifacts are a problem. For example, if you have a mass of gas bubbles, then the ring down from that can block a large area of tissue from imaging. Sometimes artifacts are useful. Sometimes they're potentially misleading. So there's a variety of different kinds of artifact, and you need to be able to recognize them, figure out whether they're real or not, which often includes manipulating the probe and looking at how they behave.